Hey everybody, we're going to be looking at topic 3, part 2, in which we're going to look at Ka, Kb, and POH and pH calculations. So pH and POH calculations. So our first point here, the acid ionization constant, Ka, is the equilibrium constant for the reaction of an acid with water. So our Ka is our products over our reactants. And Ka values are found in the right-hand column of your acid-base chart on page 8 to 9 of your data booklet. So there's on that data page there, on the right-hand side, there's all these numbers, which will start from large and go all the way down to values which are times 10 to about the negative 14. Right. Note that in this table, the first 6 acids have Ka values given as only as very large, and we know that they quantitatively react to 100% or greater than 99.9%. These acids are collectively called the strong acids because they all react quantitatively with water to form hydronium ions. All right, we're going to look at one example here in which we have hydrofluoric acid reacting with water to produce H3O plus and F minus. The equilibrium law expression is Ka is equal to H3O plus times F minus over HF. And we get a Ka of this, which you can find in your data book, of 6.3 times 10 to the negative 4. So there's 2 calculations involving the Ka constant are common for weak acid solutions. Calculating Ka value from the measured empirical amount concentration data. So if you're given some data for these values here, you can then find this value here. 2, using a Ka value to predict a concentration of hydronium ions for an aqueous solution where the initial weak amount concentration is known, which we're going to look into here. So calculating Ka from amount concentrations, let's work through an example here. So the pH of a 1.00 mole per liter solution of acetic acid is carefully measured to be 2.38 at SATP. So, my pen froze up. That's wonderful. All right. So it's found to be 2.38. This is at equilibrium. Uh-oh. Great. So we know that is at equilibrium. And step 1 tells us write the reaction of the acid with water and write the Ka equilibrium law expression. So I need to write out my reaction here. We know that it's acetic acid. This is a common one that's used just to work through some examples, and a lot of times questions come up with it. So we have CH3COH, which is aqueous, plus H2O, which is a liquid, reacting to form, what's going on here? CH3COO minus aqueous and H3O plus, which is also aqueous. And it wants us to write the Ka equilibrium law. So Ka is CH3COO minus aqueous times H3O plus over CH3COOH aqueous. So my Ka value, when I do the calculations of that, even just write the formula, how come we don't include water in that Ka expression? It's a liquid, meaning it's a pure substance, which is why it's not included. We can only have concentrations of aqueous solutions, I believe also gases, but because it's a liquid, or if it was a solid, we don't have a concentration. It has to be aqueous. All right, step 2 says find the equilibrium concentration of aqueous hydronium ion from the pH. So my H3O plus, this was in that review from the last lesson, if you watched that, is H3O plus is 10 to the negative pH, which is negative 2.38, which is equal to 0.00417. All right, step 3 is use an ice table to calculate the equilibrium concentration of the weak acid. So I write out my reaction, which is CH3COH aqueous plus H2O, which is liquid, at equilibrium, to CH3COH minus aqueous plus H3O plus. All right. We know that my initial concentration of acetic acid is 1.0 mole per liter. We just can cross everything we're going to do for H2O out. And for CH3COH, it's going to be 0 initially and 0 initially. What we found out with the information they gave us that in the last point here is that we get 0.004168. Same here for H3O plus, 0.004168, which is what's being added, so plus 0.004168. Sometimes ice tables are tedious, but they really help us break it down, make sure that we don't get screwed up. Like so, we minus that initial 0.004168, and we get 0.9958 molar per liter, like so. All right. Step 4, use your equilibrium concentrations to calculate Ka. I'm just going to go here, and you'll have to write this out, but I'm going to use a little shortcut here. Go like this. Go copy. And go paste. Oops. Move this over here. And then what I do next is I substitute my values in here at equilibrium. So Ka equals CH3CO minus, which I'm just going to go 0.004168, which is squared. This is moles per liter. Over my concentration of 0.9958 moles per liter. My Ka is a value which is 1.7 times 10 to the negative 5. All right. I am going to skip example 2, hop on to example 3. All right, this one here, our sulfuric acid, which is H2SO3 aqueous, reacting with water, which is a liquid, to produce H3O plus aqueous and HSO3 minus, like so. Make sure to include that's aqueous. Make an ice table, ICE, 0.4 molar per liter solution of sulfuric acid. This is concentration of 1.17. So initial 0.400, cross out H2O. This is at 0, this is at 0. I'm going to go 10 to the negative 1.17 to find my value, which so 10 to the negative 1.17 is 0.0676. So we're losing on this side 0.06. Pen's having issues here. 0.676. And this makes E 0.3323. Add 0.0676. Add 0.076. All right. 0.0676, 0.0676. Just a quick note, I did pull this 0.06 from up here where I calculated the pH, because even though my initial concentration is 0.40, we used the empirical evidence of the pH of 1.17 to find my concentration of hydronium ions at equilibrium. I'm really having pen issues here. All right, this is H3O plus, like so. And then my Ka equals H3O plus times HSO3 minus over H2SO3. So this is 0.0676 squared over 0.3323, and my Ka is 0.014. All right. We'll do one more example in this section, and we're going to do example 2 on the next page here. So it wants us to predict the H3O plus and pH for a 0.500 mole per liter aqueous solution of hydrocyanic acid. So we have HCN, which is aqueous, reacts with water, which is liquid, pure substance, to produce H3O plus, which is aqueous, plus Cn minus, which is aqueous, and I get 0.500. This gets crossed off. This is 0, this is 0. And then what happens next is that we don't actually have a value of, like, we don't have a pH value, so we can't just find our equilibrium value. So what we have to do is we're going to mark this as minus x. We're going to mark this as plus x. We're going to mark this as plus x. So this is going to be 0.500 minus x. This will just be x. This will just be x. So what happens is my Ka value is H3O plus times Cn minus over HCN, like so. Now I can find in the data book that my Ka is 6.2 times 10 to the negative 10. However, though, I have x squared over 0.500 minus x. All right. What we would do is we would have to multiply this to both sides. So we would, but before we even do that, we can actually we know that this value of x is going to be super small. So we'll actually just cross x off, and just that way we can simplify this down. If we don't do that, we do have to use the quadratic equation, which is the more appropriate way to do it. This is just the shortcut way, which does work about 98% of the time. The other 2%, though, is that you would have to break it down into the quadratic equation, which you would have learned in Math 20 with Mr. Erla. So H3O plus is equal to, what would happen is we'd multiply this side by 0.5, multiply this side by 0.5, and this cross off, that crosses off, and we get, and then we have to take the square root of this because we have to square root this as well. So my x value, which is my H3O plus, is equal to 1.76 times 10 to the negative 5 moles per liter. and my pH is going to be negative log of that. It gives me a pH of 4.754. Quick look at sig digs. I have 3 sig digs here. So I have 3 sig digs here. And then pH is a little weird because our sig digs are after the decimal, which is right there. All right. There's my calculations. So that's my answers for this one. And then we need to go over the base ionization constant, which I'm going to make sure that I have some notes posted for you, and then we will go over that.